What's up, guys? I'm Chad Barnes, and welcome to the channel. Here, it's all about real car talk, from simple fixes to smart driving tips and keeping your ride in top shape. If that sounds good to you, go ahead and give the video a thumbs up. Hit that subscribe button, and make sure you watch all the way through. There's a lot of good stuff coming. Let's get to it.
But not great. Any self-respecting motorist knows that at the intake stroke, air enters the cylinder. As the piston moves down to bottom dead center, the intake valves, or valve, are open and air is sucked in. And this process goes just fine as long as the valve is open. But what happens when it closes? At that point, the air suddenly stops in front of the closed door, hits it, and goes back into the intake. This may sound strange at first glance, but it's true. Air also has mass. A cubic meter of air weighs more than a kilogram, by the way, which means it's familiar with the concept of inertia. So, it returns to the intake manifold, and there it bumps into the throttle plate. And it goes back to the valve for nothing. And it would be nothing if the valve at this moment was open. In this case, more air would get into the cylinder, and therefore, if desired, it would be possible to inject more fuel. And, of course, more power. This is precisely the event that designers strive for when calculating the cross-section and length of the intake manifold. And the phenomenon in which gases inertially enter the cylinder in increasing amounts is called resonant or gas dynamic supercharging. Of course, it is peculiar only to atmospheric engines. In turbocharged engines, the necessary amount of air can be forced by the turbine. The only possible supercharging in an atmospheric motor is resonant supercharging. It is clear that you want to avoid the least favorable variant of events, to open the inlet valve at the moment when the air, having just hit the closed valve, is running from it back to the throttle valve. In this case, there will be very little air, and this will lead to very poor combustion of fuel without oxidizer, oxygen in the air. No good combustion will occur. That's why calculating the manifold is a complicated job. And, unfortunately, it involves finding a compromise. In an atmospheric engine, air enters the cylinder at about 75 to 80% of the cylinder volume. Of course, this is not entirely bad, but it is not maximally efficient either. And to make this filling more qualitative, the idea came to use resonance supercharging. But it is not so easy to do it. The frequency of this resonance directly depends on the crankshaft speed. And besides, there are two more important parameters: the mass of resonating air and its flow speed. And it is desirable to change them, because the filling of cylinders at different revolutions should have slightly different physics. If we do not go into the maze of gas dynamics, the essence can be explained quite simply. At low speeds, the air flow velocity will not be too high, which, combined with a less frequently opened valve, will lead to undesirable consequences. And if the channel is also wide, the turbulence of the air flow will be weak, which will lead to poor mixing of air and fuel. Combustion of such fuel-air mixture will not be uniform enough, and therefore inefficient. Therefore, it is better if at low speeds the length of the manifold is longer and the cross-section of its channel is smaller. At high speeds, a long and narrow duct is undesirable. Pumping losses increase too much and the potential amount of air that could enter the cylinder is reduced. Therefore, in this situation it is better to have a shorter manifold, but with a larger cross-section. In the past, they tried to come to a compromise by making a manifold that would more or less handle the airflow at both low and high RPM. As a result, the air flowed better at some speeds and worse at others, and the constant desire to make engines more powerful and environmentally friendly forced to look for ways to optimize the intake manifold. And there is only one way: to change its geometry, making it longer or shorter, narrower or wider. This is how different systems of variable intake geometry appeared. This and that the first system allows you to change the length of the intake manifold depending on the RPM. It is often referred to as variable intake length. The principle of its operation is quite simple. The manifold has two channels of different lengths. There is a damper in it, which can switch the air flow either to the long channel or to the short one. It is clear that there is also some assumption here. Instead of smoothly changing the length of the intake, there are only two positions of its length. Yes, the solution again smells of compromise, but it's still better than nothing, and it would be very expensive to make a system that would change the length of the manifold continuously depending on the revs. Theoretically such systems exist, but in life they are very rare. The question remains, who controls all this and how? In the most primitive systems, of course, the rarefaction in the manifold, which drops with increasing revolutions. In this case, a simple actuator is used which changes its position under the action of a diaphragm. This mechanism is not too accurate and almost impossible to diagnose, so another principle is more popular: electric drive controlled by ECU. It works more accurately, and in case of emergency it is able to light up check engine and ask for computer diagnostics. Changing the cross-section of the inlet duct works on much the same principle. Either there is a damper that stands in the duct and changes its cross-section, or if there are two ducts, it can block one of them. Controlling these dampers is the same as controlling variable length dampers, either by vacuum or electric actuator. To be fair, it should be added that switching between channels is not always controlled by a damper in the literal sense of the word. Something like a plate that rotates on an axis. The realization can be different, and, for example, in Opel's Z18 XER engines this process is managed by the so-called drum, which, to be honest, does not look like a drum at all, standing inside the manifold. It has windows and the ability to rotate around its axis. Depending on the angle of rotation of the drum, its windows can be partially blocked by a blind wall and can be open, which changes the speed and volume of airflow. Yes, Opel was once able to please with a non-standard approach to standard things. Why did I bring up Opel? Because many manufacturers try to add uniqueness to their intake geometry modification systems, but technically it doesn't look very interesting. They all look alike. That's why marketing and invention of new names are used. Hence, we get some mess of letters in which it is easy to get confused. For example, Ford's system of changing the cross-section could be called IMRC, Intake Manifold Runner Control, or CMCV, Charge Motion Control Valve, and its system of changing the intake length is called DSI, Dual Stage Intake. In BMW this system is called DIVA, Differential Variable Air Intake, and so on. There are many different abbreviations, but the essence of them is the same. To be more exact, change of length or cross-section. However, there are some systems that change both at the same time. What can go wrong? The weak point of variable geometry is the flaps. Rotating on the axis, they wear out and over time begin to play. There is a characteristic knocking, or even cracking, in the area of the intake manifold. If you look at this unpleasant phenomenon through your fingers, the flap at one point may fall apart, after which its pieces will fly straight into the cylinder. And that would be very sad. Also, the flaps can get sooty over time. We remember the beautiful air recirculation system that can send some of the exhaust gases into the intake. It also sends soot particles into the intake. If there's a lot of soot, the flaps will become overgrown with it and stop working properly. This is where flushing will help, for which, unfortunately, the intake will have to be disassembled. Other symptoms indicating a faulty variable geometry intake are not able to unambiguously point to it. There will be a noticeable increase in fuel consumption. In some modes the power will be reduced. But here you cannot do without diagnostics. There are many reasons for such ugliness, and the intake geometry is almost in the last place. Well, it is better not to drive with cracking of flaps. Consequences of their debris for the motor are almost fatal. More often vortex flaps fly into the intake, but nevertheless incomprehensible knocking and cracking in the manifold should immediately alert you. In conclusion, variable intake geometry is a game-changing technology that optimizes airflow into the engine, enhancing performance and efficiency without the need for additional boost. By adjusting the intake path based on engine speed and load, it ensures that your engine receives the right amount of air at all times, leading to improved power output and fuel economy. Understanding and implementing this technology can significantly elevate your vehicle's performance, making it a valuable consideration for any automotive enthusiast or engineer. Thank you for watching, and we hope you gained valuable insights into the benefits of variable intake geometry.